This module on effective instruction in mathematics across tiers will be divided into 3 parts. This module focuses on effective Tier 1 instruction. This is the first of 3 modules and should take 35 minutes to view. This module is divided into 3 separate sections. Foundations for Effective Math Instruction, which will take approximately 11 minutes to view. Evidence-Based Practices for Math, which is approximately 14 minutes. And Using Data to Identify Tier 1 Effectiveness and Concerns, taking approximately 10 minutes to view. The overall viewing time is 35 minutes for this module. Statistics from the U.S. Department of Education 2008 show that 78% of adults cannot explain how to compute the interest paid on a loan. 71% cannot calculate miles per gallon on a trip, and 58% cannot calculate the tip for a lunch bill. Tier 1 is the core instruction that all students receive and is based on the Florida Standards. Educational equity, or the access to the Florida Standards, is provided to all students, regardless of their personal characteristics, backgrounds, or physical changes. Mathematics in Florida is based on key concepts. The expectation is that all students engage in and are proficient with the Florida Standards. Instruction is based on evidence-based practices, and an assessment system has been implemented to support the measurement of student progress in response to Tier 1 instruction. The Florida Standards are housed on CPALMS and can be found at www.cpalms.org. CPALMS is an online toolbox of information, vetted resources, and interactive tools that help educators effectively implement teaching standards. It is the state of Florida's official source for standards information and course descriptions. CPALMS also provides 16 state-of-the-art curriculum planning and professional development apps and tools to help educators effectively implement the standards. The Florida Math Standards were developed with foundational basis from multiple resources, including the 8 Standards for Mathematical Practice from the Common Core Standards, the National Council of Teachers of Mathematics Content and Process Standards, and the Principles for High-Quality Mathematics Education, as well as the National Research Council's 5 strands of mathematical proficiency, which we will briefly discuss in the following slides. The Standards for Mathematical Practice describe ways in which mathematics students ought to engage with the subject matter as they grow in mathematical maturity and expertise throughout the elementary, middle, and high school years. The Standards for Mathematical Practice describe varieties of expertise that mathematics educators at all levels should seek to develop in their students. These practices rest on important processes and proficiencies, with long-standing importance in mathematics education. The first of these are the NCTM Content and Process Standards, the second of the strands of mathematical proficiency specified in the National Research Council's report, Adding It Up. Both of these primary resources will be touched on briefly and are available in the handouts and resources that make up this module, as well as additional resources regarding the mathematical practices, including examples of what the standards look like in the classroom and a student-friendly poster to provide the relevance of these standards to students. The National Council of Teachers of Mathematics has identified a comprehensive set of standards known as the Mathematics Content and Process Standards for all students. The standards are descriptions of what students should know, understand, and be able to do in mathematics. In 2001, the National Research Council, or NRC, of the National Academies of Science published a report titled Adding It Up, Helping Children Learn Mathematics. The report addressed the latest educational, psychological, and neurological research about teaching for mathematics proficiency, focusing on the interactions between teachers and students around educational materials and how teachers develop proficiency in teaching mathematics. Their work significantly influenced subsequent research as well as the pedagogical and curricular aspects of teaching of mathematics from kindergarten through community college. In the report, the NRC chose the term mathematical proficiency to capture what it means for anyone to learn mathematics successfully. Mathematical proficiency consists of the following 5 components or strands. Adaptive reasoning, which is the logical thought, reflection, explanation, and justification. Strategic competence, which is formulating, representing, and solving. Conceptual understanding, or the comprehension and connection of mathematical concepts. Productive disposition, which is seeing math as useful and worthwhile, and one's own efficacy with mathematics. Procedural fluency, or the skill to effectively and efficiently carry out procedures. Additionally, the National Council of Teachers of Mathematics has identified 6 principles or features for high-quality mathematics education. Equity, which is the high expectations and strong support we have for all students. Curriculum, which is coherent and focused on important mathematics and well articulated across grade levels. Teaching, or the understanding of what students know and need to learn. Learning, actively building new knowledge from experience and prior knowledge. Assessment, or the support of the learning of new mathematics, which is informative to teachers and students. And technology, which influences the math taught and enhances students' learning and motivation. When unpacking the Florida standards, it's obvious that the standards for mathematical practice, NCTM's content and process standards, and the 5 strands of mathematics proficiency have influenced the creation of the standards and been utilized as foundations and embedded throughout. What does effective instruction look like in math? Here are several key concepts that should be present in every math classroom, although this is not an exhaustive list. Utilization of tools and technology. Manipulatives such as base 10 blocks and those found on the National Library of Virtual Manipulatives. Content knowledge of the teacher. The teacher must have strong understanding of the content, both the concepts and skills, and be able to translate those to the students, as well as knowledge of how students learn and typical barriers. Teaching for conceptual understanding, developing procedural literacy, and promoting strategic competence through meaningful problem-solving investigations. Providing real-world examples, which is something the students can relate to, such as the math behind creating a skateboard ramp. Encouragement of divergent thinking. Students need to be encouraged to find multiple ways to solve problems. There's more than one way to find an answer. Examples can be found on CPOMs. Posing challenging questions and making interdisciplinary connections and examples. There are many excellent resources online and in the state. CPOMs is where we will be referred to many times throughout this module. The concrete to representational or pictorial to abstract approach is a 3-step instructional approach that has been found to be highly effective in teaching math concepts. The purpose of teaching through a concrete to representational to abstract sequence of instruction is to ensure students have a thorough understanding of the math concepts and skills they are learning. When students who have math learning problems are allowed to first develop a concrete understanding of the math concept or skill, then they are much more likely to perform that math skill successfully and truly understand math concepts at the abstract level. Each math concept or skill is first modeled with concrete materials or manipulatives such as Unifex cubes, base 10 blocks, beans, sticks, or pattern blocks. Students are provided many opportunities to practice and demonstrate mastery using concrete materials. The math concept or skill is next modeled at the representational or pictorial level, which is the semi-concrete level and involves pictures that represent the concrete objects previously used, such as graphs, tallies, dots, circles, stamps, that imprint pictures for counting. The students are provided many opportunities to practice and demonstrate mastery by drawing solutions. The math concept or skill is finally modeled at the abstract level using only numbers and mathematical symbols. Students are provided many opportunities to practice and demonstrate mastery at the abstract level before moving to a new math concept or skill. As a teacher moves through a concrete to representational or pictorial to abstract sequence of instruction, the abstract numbers and/or symbols should be used in conjunction with the concrete materials and representational drawings, which promotes association of abstract symbols with concrete and representational understanding. The final report of the National Mathematics Advisory Panel was released in 2008 by the U.S. Department of Education. Recommendations from the report have been utilized to drive instructional practice and tools for both instruction and intervention in mathematics. One recommendation was that educators must focus mathematics to meet the critical foundational needs. Many students that struggle have deficits around foundational math concepts. Another recommendation was that when designing and delivering core instruction, educators must embed explicit instruction as well as strategy instruction, which develop conceptual understanding. Explicit instruction, often called direct instruction, refers to an instructional practice that carefully constructs interactions between students and their teacher. Teachers clearly state a teaching objective and follow a defined instructional sequence. They assess how much students already know in the subject and tailor subsequent instruction based upon that initial evaluation of student skills. Students move through the curriculum both individually and in groups, repeatedly practicing skills at a pace determined by the teacher's understanding of the student's needs and progress. Strategy instruction refers to the strategies students learn that help them integrate new information with what is already known in a way that makes sense, and then they are able to recall the information or skill later, even in a different situation or place. Conceptual understanding will be addressed in upcoming slides. Additional resources regarding the National Math Panel's recommendations are available in the resource section of the module. We will address each of these in the upcoming slides regarding evidence-based instruction. One of the most important ways of ensuring access to core instruction for all students is through the use of validated instructional approaches. Explicit instruction is recommended and endorsed by the U.S. Department of Education and the National Council of Teachers of Mathematics. Explicit instruction has been found to be especially successful when a student has problems with a specific or isolated skill. The Center for Applied Special Technology, or CAST, offers a helpful snapshot of an explicit instructional episode shown in this figure. Consistent communication between the teacher and student creates the foundation for the instructional process. Instructional episodes involving pacing a lesson appropriately allow adequate processing and feedback time, encouraging frequent student responses and listening and monitoring throughout a lesson. Here are some essential components of explicit instruction identified. The teacher breaks down the math concept or skill into critical features or elements and learnable parts. The teacher clearly describes features of the math concept or steps in performing the math skill, then models the math concept or skill. The teacher describes and models using multi-sensory techniques such as visual, auditory, tactile, and kinesthetic. The teacher thinks aloud as he or she models and provides modeling examples and non-examples. The teacher provides cues or prompts for the students and also provides high levels of interaction by engaging the students in learning through demonstrating enthusiasm, maintaining a lively pace, periodically questioning students, and through checking for student understanding. Here is an example of direct instruction for mathematics. The teacher is providing step-by-step instruction of the concept when teaching addition of decimals. The teacher begins with a review of adding integer numbers and includes the importance of lining up the ones column and then lining up each column to the left. Next, they review the meaning of the decimal point. The teacher demonstrates how the decimals must be lined up and models problems that require the addition of decimals several times, talking through each problem. The teacher applies the skill to practical situations, such as adding money. And finally, the teacher allows the students to practice a variety of addition problems, some involving skills the students have already mastered and some using the new skill. When the students achieve mastery, determined through continuous progress monitoring, the teacher will move on to the next skill, but continue through practice to reinforce earlier skills. One effective approach to assisting students that struggle in mathematics to access challenging mathematical concepts is to provide strategy instruction. Strategy instruction involves teaching strategies that are both effective, They assist students with acquiring and generalizing the information. And efficient. They help students acquire the information in the least amount of time. Systematic instruction focuses on teaching students how to learn by giving them the tools and techniques that efficient learners use to understand and learn new material or skills. Systematic instruction, sometimes called strategy instruction, refers to the strategies students learn that help them integrate new information with what is already known in a way that makes sense and be able to recall the information or skill later, even in a different situation or place. Typically, teachers model strategy use for students, including thinking aloud through the problem-solving process, so students can see when and how to use a particular strategy and what they can gain by doing so. Systematic instruction is particularly helpful in strengthening essential skills, such as organization and attention. A strategy refers to a plan that not only specifies the sequence of needed actions, but also consists of critical guidelines and rules related to making effective decisions during a problem-solving process. Strategy instruction is beneficial, particularly for struggling students in mathematics. Memory devices help students remember the strategy, such as a first-letter mnemonic, which is created by forming a word from the beginning letters of other words. Strategy steps that use familiar words, stated simply and concisely, and begin with action verbs to facilitate student involvement, such as reading the problem carefully. Strategy steps that are sequenced appropriately, such as when students are cued to read the word problem carefully prior to solving the problem and lead to the desired outcome, which is successfully solving a math problem. Strategy steps that use prompts to get students to use cognitive abilities, such as the critical steps needed in solving a problem. And metacognitive strategies, which use prompts for monitoring problem-solving performance. Students will ask themselves, did I check my answer? Some strategies combine several of these features. The example you see is STAR, which is an example of an empirically validated first-letter mnemonic and can help students recall the sequential steps from familiar words used to help solve word problems involving integer numbers. The steps for STAR include S. Search the word problem. T. Translate the problem. A. Answer the problem. And R. Review the solution. A graphic organizer such as this Freyer model is an example of strategy instruction that can be utilized for math or any other content area. The Freyer model is a strategy that uses a graphic organizer for vocabulary building. This technique requires students to first define the target vocabulary words or concepts, and second, apply this information by generating examples and non-examples. The information is placed on a chart that is divided into 4 sections to provide a visual representation for students. This instructional strategy promotes critical thinking and helps students to identify and understand unfamiliar vocabulary. The Freyer model can be used with the entire class, small groups, or for individual work. It draws on a student's prior knowledge to build connections among new concepts and creates a visual reference by which students learn to compare attributes and examples. Direct instruction and strategy instruction assist in developing students' conceptual understanding in mathematics. NCTM acknowledges that the need to understand and be able to use mathematics in everyday life and in the workplace has never been greater and will continue to increase. Therefore, instruction needs to be carefully planned and delivered to address conceptual understanding. Conceptual understanding is the ability to understand the concepts and recognize their applications in various situations. It is the comprehension of mathematical concepts, operations, and relations, the knowing of what mathematical symbols, diagrams, and procedures mean. It enables you to connect ideas to what you already know, supporting retention and preventing common errors. The elementary example seen here is 20 plus 70 equals. The use of zeros with place value problems is simple but critical for understanding. What is 20 plus 70? A student who can effectively explain the mathematics might say 20 is 2 tens and 70 is 7 tens. So 2 tens and 7 tens is 9 tens. 9 tens is the same as 90. The middle school example shown here is fractions, decimals, and percents integrated in problem situations. What is 25% of 88? Rather than multiplying 0.25 times 88, conceptual understanding of this problem might include 25% is the same as 1/4, and 1/4 of 88 is 22. Concepts are integrated to find the answer. Some ways to build conceptual understanding are using manipulatives to model concepts and verbalize results, showing multiple representations of the same mathematical situation, and the use of prior knowledge to generate new knowledge and to use knowledge to solve problems in familiar situations and unfamiliar situations. As noted by the National Research Council in 2001, when students have conceptual understanding of the mathematics they have learned, they avoid many critical errors in solving problems, particularly errors of magnitude. When thinking back to where we started regarding educational equity for all students in mathematics, access and attainment for all students can and will occur when the principles of universal design for learning are employed in mathematics across all tiers of instruction. Universal Design for Learning, or UDL, is a framework to improve and optimize teaching and learning for all students based on scientific insights into how humans learn. The UDL guidelines represent three networks: the recognition, strategic, and affective networks of the brain. The purpose of UDL is not simply to help students master a specific body of knowledge or a specific set of skills, but to help them master learning itself. In short, to become expert learners. Expert learners have developed three broad characteristics. They are to be strategic, skillful, and goal-directed, to be knowledgeable, and to be purposeful and motivated to learn more. Designing curricula using UDL allows teachers to remove potential barriers that could prevent learners from meeting this important goal. The first principle of UDL is providing multiple means of representation. Students are provided with options for accessing the instruction. Some of the examples that are represented here are mathematical concepts connected to literature, video examples of a concept such as brain pop, an example of an image that is portrayed in a math vocabulary example for a right angle, a virtual manipulative website, and a geometry website that provides real-world applications of concepts. The second principle of UDL is providing multiple means of action and expression. Students are provided with the options to demonstrate their responses and their learning. Here you will see examples of student work in Kentucky's Montgomery schools. A presentation full of UDL examples in mathematics from Montgomery schools is available in the resource section of the module. The third principle of UDL is providing multiple means of engagement. Individual choice in mathematics is very powerful. Allowing students to decide how they want to interact and engage with math concepts can be the pivotal point between students loving and hating math. Providing options for students and allowing them to collaborate with their peers, as well as optimizing their motivation with setting attainable goals, can turn a struggling math student into a successful math student. UDL provides a blueprint for creating instructional goals, methods, materials, and assessments that work for everyone, not a single one-size-fits-all solution, but rather flexible approaches that can be customized and adjusted for individual needs. Individuals bring a huge variety of skills, needs, and interests to learning mathematics. These learning differences are as varied and unique as fingerprints. Options must be embedded to ensure equity for all students to the core instruction. All students must have opportunities to study and support to learn mathematics. Equity does not mean that every student should receive identical instruction. Instead, it demands that reasonable and appropriate accommodations be made as needed to promote access and attainment for all students. Additionally, differentiating instruction through content process and/or product is one approach. This is a particularly powerful approach when flexible and targeted grouping is employed. Instructional decisions must be made through the ongoing collection of purposeful data. It is imperative to utilize data effectively and efficiently to identify any concerns around students that may be struggling. Following the collection of data, the team must determine whether a systematic problem exists. Where systematic learning problems are identified, the core program of instruction should be evaluated to ensure that a research-supported curriculum is being used, that instruction is being delivered for sufficient duration and with sufficient quality, and that adequate resources are available to support effective instruction. Various types of data may be collected to get a clearer picture of what is happening in the math classroom. Screening measures are assessment tools designed to collect data for the purpose of measuring the effectiveness of core instruction and identifying students needing more intensive intervention and support. The Center on Response to Intervention houses a screening tools chart and is located at the URL listed here. Diagnostic measures are the formal or informal assessment tools that measure skill strengths and weaknesses, identify skills in need of improvement, and assist in determining why a problem is occurring. Diagnosis is an integral part of instructional decision making. As the bridge between identification of students who may be at risk for failure and delivery of carefully designed supplemental interventions, diagnosis provides valuable information about students' persistent misconceptions in the targeted domain. Progress monitoring measures are the ongoing assessments conducted for the purposes of guiding instruction, monitoring student progress, and evaluating instruction and intervention effectiveness. A common math screening measure, which can also be used for ongoing progress monitoring, is curriculum-based measurement, or CBM. Intervention Central provides free CBMs for math across grade level and is listed at the URL listed here. Formative measures are those ongoing assessments embedded within effective teaching to guide instructional decisions. They are used for the purpose of forming or guiding instruction and might include observation, conversation, journal writing, and daily work. The Great Schools Partnership provides 25 quick formative assessments for a differentiated classroom at the URL listed here. Summative or outcome measures are those typically administered near the end of the school year to give an overall perspective of the effectiveness of the instructional program and student mastery of concepts. Examples of these for math include the Math Florida Standards Assessment, or FSA, and the End of Course Assessments, or EOCs. Hyperlinks for both the Math FSAs and EOCs are listed here. CPALMS also houses the Mathematics Formative Assessment System, or MFAS. MFAS includes tasks or problems that teachers can implement with their students and rubrics that help the teacher interpret students' responses. Teachers using MFAS ask students to perform mathematical tasks, explain their reasoning, and justify their solutions. Rubrics for interpreting and evaluating student responses are included, so that teachers can differentiate instruction based on student strategies instead of relying solely on correct or incorrect answers. The objective is to understand student thinking so that teaching can be adapted to improve student achievement of mathematical goals related to the Florida standards. Here is an example of a typical 7th grade mathematics CBM probe. Skills measured on this probe represent the year's curriculum and include addition, subtraction, multiplication, and division of complex whole numbers and rational numbers. Students have an average of 4 minutes to complete as many items as possible. The score report for this probe indicates the number of items on the probe that measure each subskill, the student's score, and associated skill analysis. The score report for this probe indicates the number of items on the probe that measure each subskill, the student's score, and associated skill analysis. As indicated, the summary judgment for the skill analysis is based on minimal student response data. Although skills analysis may provide teachers with useful information to support subskill mastery, student performance on this probe may or may not be indicative of persistent misconceptions that need remedial instruction. This example represents possible student responses to a sampling of items from the CBM probe presented previously. Error analysis can provide timely information for adjusting instruction so as to avoid reinforcing incorrect procedures. Let's look at an example of a common challenge and how we can apply the problem-solving process. It doesn't take long for most mathematics teachers to discover that their classrooms are filled with a diverse cross-section of students. Students arrive in the classroom with varying abilities, learning styles, and learning disabilities. Common challenges may still arise in the math classroom, irrelevant of all of the wonderful things happening. An analysis of the data will provide insight into where the challenges are occurring. One common challenge is that students may have difficulty solving word problems. The problem-solving process is critical to making the instructional adjustments needed for continual improvement in both student level of performance and rate of progress, as well as critical for assessing the effectiveness of the instruction and interventions provided. Throughout the continuum of instruction and intervention, problem solving is used to match instructional resources to educational need. The 4 steps of the ongoing problem-solving cycle are to define the problem, to analyze the problem, to develop and implement a plan, and to measure response to instruction and interventions. In the resource section of this module, you will find a guiding questions for problem-solving document. This tool provides more detailed questions to consider by the team as they are going through this process. The following slides will provide only a brief overview. Step 1 is to define in objective and measurable terms the goal or goals to be obtained. During problem identification, we need to determine what specifically it is that we want students to know, understand, and be able to do. What do they currently know, understand, and are able to do, and what exactly is the problem? In our example, the students are having difficulty solving word problems involving fractions, which aligns to these 2 Florida Math standards. Next, step 2 is problem analysis. We need to identify possible reasons why the desired goal or goals are not being attained. Why are students not meeting the performance goals? What are the barriers? We need to generate a hypothesis or hypotheses. We would at this point gather assessment data to validate or invalidate the hypothesis or hypotheses. When interpreting data, the data team should utilize data from various sources. The team should be comprised of various stakeholders that have both content and pedagogical expertise, such as the general education and the special education teachers, as well as the math coach. The meeting should be a collaborative discussion among team members regarding student achievement and instruction. They will use the data to measure the intensity of the problem. An error analysis, similar to what we discussed earlier, should be utilized to determine specific skill deficits and barriers to successfully meeting performance goals. Then, step 3 regards developing and implementing a well-supported plan involving evidence-based strategies to attain the goal. What are we going to do? Establish a performance goal. Develop an intervention plan to achieve the goal. Determine how progress will be monitored and fidelity supported. Our plan will need to include strategies such as highlighting keywords, having the student restate the problem, providing concrete examples using manipulatives, providing pictorial or representational examples, and connecting to the abstract representation of the word problem. Finally, step 4 is measuring the response to instruction and intervention. We will evaluate the effectiveness of the plan based on students' response to determine, is what we put in place working? If not, how will the instruction or intervention be adjusted? If it is determined by the team that a group of students would benefit from additional supports beyond core instruction and intervention, then Tier 2 supports are put into place. The next module regards Tier 2 instruction for math. The resources referred to throughout this module are available on the resource list, which includes additional resources broken down by topic.